Okay.
Okay, my name's Greg Croft. For those of you that don't know me, I've been here or worked here for like 36 years. I retired about 5 months ago. Retirement's very good. Today's talk is an introduction to electronic memories, and I'm going to talk about fuses, anti-fuses, latches, flip-flops, registers, DRAMs, SRAMs, EPROMs, double EPROMs, core memory, FRAM, and ReRAM. So there's a lot to talk about today. So most ICs incorporate some type of memory, and analog memory can include such things as hysteresis or delay lines, where the present behavior of the chip is affected by past events. Digital memory is basically stored logic ones and zeros. So today's talk, I plan on concentrating just on the digital memory. However, you may notice some analog concepts sneaking in there every so often. So I'd like to start by talking about simple fuses and latches, and then transition to devices and networks dedicated to the mass storage of digital bits. I'd also like to cover some obsolete and some emerging technologies to give you a feeling of where we've been and maybe where we're going in memory. So one-time programmable, that's OTP fuses, are used on many integrated circuits to store manufacturing settings, such as trim bits for analog circuitry. These fuses are typically made using polysilicon or a thin film metal like cychrome. One of the main advantages of these fuses is they're non-volatile. This means they retain data even when power is removed. Now, it's common for the fuse bits to be read during power up, and then that data to be stored in digital registers. The register bits are what's used to actually define the manufacturing settings. This scheme allows the test engineer to try out different patterns in the register before committing to actually blowing the fuses. And this technique is known as try before you buy. Probably everyone here is familiar with it. I highly recommend it. So the procedure for blowing the fuses is fairly straightforward. The fuse starts off with a reasonably low resistance value, somewhere like 100 ohms. Then you apply a designated current or voltage pulse for a selected amount of time, causing an area of the fuse to overheat and vaporize, scattering the conductive material into the surrounding oxide. Nothing actually blows out through the top of the IC or disrupts the passivation. This procedure increases the resistance of the fuse by a few magnitudes. The fuses are read by applying a voltage or current and comparing the resulting current or voltage against a reference. Pretty straightforward. Now I'd like to talk about anti-fuses. An anti-fuse is exactly the opposite function to a fuse. Instead of creating an open, we're creating a short. And one of the well-known types of anti-fuses is called Zener Zap. Now, I don't think this is used very much anymore, but it was used for a long time on many analog products. So Zener zapping is a process that typically uses a Zener diode to permanently adjust analog circuits. And it's kind of like a fuse trim bit. It involves overloading the PN junction with a reverse current spike that causes the junction to overheat and short out. Often the base emitter diodes of bipolar transistors were used. And if you look in the lower left corner here, you can see here's a trans diode, a bipolar device hooked up as a trans diode. The base emitter diode here is it's pretty much a Zener. It's like a 7-volt breakdown. Well, if you crammed a current spike through that, and that current spike was big enough that you could heat that junction up, you could migrate the metal and short out this diode, causing it to look like a low-value resistor. Here's a cross-section of that bipolar transistor. And what you're trying to do is you're trying to heat this junction up and then take some of this metal and migrate it down through and short the junction out. This process was often used to trim the value of analog components. And for example, let's look at this circuit off to the side here. The offset voltage of this amplifier can be trimmed by altering the value of each of these resistor strings. So we've placed some probe pads such that reverse current spikes can be forced on any combination of these Zener diodes. So shorting out various resistors can trim the offset voltage either up or down as needed. Now, just an aside, you might notice the values of these resistors, they're binarily weighted, R, 2R, 4R, we do that just so you can get more trim range with fewer number of bits. Next topic, digital latches. So a latch can be thought of as a 1-bit memory cell. And there's lots of ways to build a latch. However, one simple way to understand how they work is shown here. The switches in this schematic would actually be implemented as transmission gates. Data is brought in on the D input, that's right here. And if the control input is high, the switches are in the position shown in this diagram. And this puts the latch in transparent mode. And in transparent mode, data coming in goes right through inverters 1 and 4 and appears right on the Q output. So this latch is, as far as the truth table goes, is right here. In transparent mode, the data on D goes right through and comes out on the Q output. However, placing a low on the control input alters the state of the latch as shown here. This is now the latch state. This switch S1 opens, it blocks any new data from entering, and now the old data is held in a loop here, formed by these two, I guess, anti-parallel inverters, one feeding the other. And those inverters are going to hold that state until the control input changes or you power the part down. So this is basically a 1-bit static memory, meaning it doesn't need to be refreshed. It's going to sit there forever until power is lost. This is known as volatile memory because if you power down, the bit goes away. So a flip-flop is another type of 1-bit digital memory cell. And there's several types of flip-flops out there. However, I'm going to concentrate on the delay or D flip-flop, abbreviated DFF. So D flip-flops are similar to a latch. However, they don't have a transparent mode. Instead, D flip-flops only allow the output to change on the rising edge of the clock signal. And you can see we have the symbol of a D flip-flop down here of what the truth table of a D flip-flop looks like here. But if it's not the rising edge, the output is staying at whatever the previous value was. This rising edge triggered operation can be accomplished using 2 latches in a master-slave arrangement, as I show down in the lower right corner here. And there are several ways to draw the schematic for a D flip-flop. I'm showing the transmission gate version because I believe it's easier to understand. There are other ways you can draw these with different logic gates. So when the clock is low, the switches are positioned as shown here. And in this mode, the master is transparent and it's sampling the D input, and the slave is latched. And the slave is holding the previous sample data and outputting it on the Q output. So that would be this part of the truth table right here. So again, the master is transparent and the slave is latched. As the clock rises, the switches change position. The new incoming data is blocked because you open switch S1, and the current sample data is now latched into the master. And the slave enters transparent mode, which sends the current sample data straight through and out onto the Q output. So eventually the clock's going to start falling again. And when it falls, the sample data latches and the master becomes transparent again. And this whole cycle starts all over again. So that shows you just how an edge-triggered flip-flop works. So D flip-flops can also have a couple other pins. We have a set, a reset, and a Q bar. And the Q bar is just the inverse of the Q output. So the set and reset, if they're both low, the flip-flop functions normally. However, if set or reset is high, the flip-flop's outputs are forced to a state per this truth table. So you can use the set or reset to actually force the output one way or the other. Using the set or reset pin is often used during power on reset, or POR, as it's commonly called, to force all the flip-flops into a known state. When you power up, you'd like all your memory bits to start out in a known state. So a D flip-flop acts as a 1-bit memory. What if you want more than 1 bit? Well, you can actually just add additional flip-flops and create a register. So here's a simple 4-bit parallel in, parallel out register. So on the rising edge of the clock, this register reads the state of this 4-bit bus line and then holds that state on its output until the next rising edge of the clock. I think this is very straightforward. Shift registers, serial in, serial out register shown here is known as a shift register. New data is brought in on the rising edge of every clock. And as the clock cycles, data gets shifted to the right, one position every time a clock edge comes through. So after 4 cycles, the original data appears on the output over here. Shift registers are often used in applications where you need to limit the number of input or output pins. If you increase the number of bits, there's no increase in pin count here. This concept is commonly used for serial interfaces like SPI or I2C interfaces. Counters. Counters are another useful circuit that can be created using D flip-flops. The circuit below is a 3-bit up counter. So this configuration is known as a ripple counter. And no data that's not referring to how many times you've been to ABC Liquor last week. Okay. So you start by resetting all the flip-flops. And this forces all the B outputs to 0 and all the inverting outputs to 1. Now you apply a string of clocks to the first flip-flop here. As the clocks arrive, the B outputs change and produce a binary count. And you can kind of look over here. On the first edge, the count is 0. On the on 0th edge, on the first edge, you end up with a count of 1. On the second edge, you end up with a count of 2, and this is counting in binary. So on the 7th clock, you're at a binary 7, and on the 8th clock, this flips back around and starts at 0 again. So this is just letting you know something else you can do with flip-flops that's kind of interesting. So with a minor adjustment, this circuit can be turned into a down counter. And so the hookup is a little different now, but now we start by setting all the flip-flops. And when you set it, it forces all the B outputs to 1. So once again, we bring in a string of clocks. However, now on every rising edge of the clock, the count will decrease by 1 instead of increasing by 1. And you can see now we start with a count of 7. And as we see clock edges, it counts down to 0. And on the 8th rising edge, it'll flip back around and start up here at 7 again. So just giving you an idea of different things you can do with counters. Counters can also be used as a frequency divider. So if the clock inputs are driven with a periodic square wave, the waveforms for B0, B1, and B2 are shown below here. So you have your incoming clock, and then the different outputs of each flip-flop. So you can see that each stage of the counter divides the frequency by 2. For example, let's say you have an oscillator running at 8 megahertz. However, you have other circuitry you want to run at 1 megahertz. Rather than make a second oscillator, you can just use this ripple counter to generate the 1 megahertz you need by dividing down the original clock signal. So it's kind of convenient if you need to reduce your frequency. Now we're getting into some of the masked storage devices. I'll talk about DRAM first. DRAM stands for Dynamic Random Access Memory. And I think we're probably all familiar with the sticks of DRAM used in modern personal computers. In addition, many gaming consoles such as PlayStation, Xbox, Wii, and some of the newer consoles make extensive use of DRAM. DRAM is a type of volatile random access memory where each bit of data is stored as a little charge on a capacitor. So over time, the charge in these capacitors will leak off. So this type of memory needs to be periodically refreshed. This refresh requirement is where the term dynamic comes from. The advantage of DRAM is in its structural simplicity. Only 1 transistor and 1 capacitor per bit, compared to typically 6 transistors for static RAM. So this allows DRAM to have an extremely high packing density with billions of bits per chip. So the basic memory cell is shown in the lower right corner here. or absence of the charge on this capacitor indicate a binary 1 or 0. This transistor here acts as a switch for reading or writing the data to and from the capacitor. Now, generally, DRAM memory cells are arranged in square arrays. You have row and column addresses to access individual bits. Sense amplifiers, which are similar in function to a comparator, can be used to determine if the selected capacitor is charged or not. And in refresh mode, the charge of each capacitor is sensed and then rewritten many times over per second. All this reading, writing, and refreshing of the data requires a reasonable amount of support circuitry around the main memory array. However, since the memory array can be made very small, DRAMs have a size advantage over many other types of memory. So let's take a more detailed look at how a DRAM array is typically structured. So you have word lines that address the rows. All these lines that run left to right are called word lines. And then you have bit lines that address the columns. The vertical lines here are the bit lines. And it's common for a DRAM array to be divided into two halves, with half the bit lines on top and half the bit lines on bottom. And you can see each sense amp looks at one bit line on top and one bit line on bottom. This architecture optimizes the use of a differential sense amp for reading and refreshing the data. And I'm going to explain, or try to explain how that works. Okay, so let's say we want to read the value of charge on this capacitor C1. Well, what you end up having to do is you can't just read this one bit, you end up having to read this entire row. So before we read the rows, we start by setting all the bit lines, that means all these vertical lines, we pre-charge them to VCC over 2. All the top bit lines get charged to VCC over 2, and all the bottom bit lines also get pre-charged to VCC over 2. Now you energize the red word line. So that connects each of these capacitors on this row to its corresponding bit line. So the charge on all those capacitors are going to slightly alter the voltage on the bit line they're connected to. And the sense amp now looks at that bit line and the one on the bottom that was pre-charged that hasn't been messed with, and it looks for that slight difference between the top bit line and the bottom bit line. So each sense amp detects this small delta voltage between the top and the bottom, and then latches that digital value and drives each bit line to the full voltage level, either a logic 1 or logic 0, whatever it detected. So reading the data on each cap in the row is destructive. You're pulling the charge off of it. However, the latching action of the sense amp replaces that data back onto each cap. So now the desired bit line 1 can now be read, using a mux. You just mux out the one that you wanted. So let's say we want to write to this specific location. Well, we start by doing the read operation that we just talked about. So after the sense amp has detected the value on this cap and then replaced it, now you come up here and you turn on your driver on that line. And if the sense amp is still driving it, you can overdrive it using the bit line driver. It's much more powerful than the driver of the sense amp. And now you can put whatever value on that cap you want. Normally, these bit line drivers up on top are tri-stated. You only turn them on when it's time to write. So that's just how to write a bit. The next topic is SRAM, and this stands for static RAM. And the basic 6-transistor static RAM cell is shown right here. We have our bit line and our word line, but now we have an extra bit line bar. It's just the opposite logically of the bit line value. And we have an inverter pair, that's very similar to that anti-parallel inverter we saw in a latch before. It'll hold the value of whatever bit you put in here as long as the circuitry is powered. The pass transistors on the left and right here are just there for sensing or writing this bit that's being held by these anti-parallel inverters. No refreshing of this bit is required because these inverters are going to hold the bit. However, the data will be lost if the circuit is powered down. So this type of memory is volatile. And again, like I said, the pass transistors on the left and right are used as switches for reading and writing the data. So similar to DRAMs, SRAMs are arranged in a rectangular array with word lines and bit lines used to access individual bits. We have a differential sense amp used during the read process, and it's pretty similar to the sense amp in the DRAM. However, the sense amp in the SRAM is now connected between the bit line and the bit line bar, instead of being connected to two different bit lines in the DRAM where you had a bit line on the top of the array and a bit line on the bottom of the array. Since reading is non-destructive in an SRAM, the main job of a sense amp is not to do any refreshing, it's there to enhance the speed of the SRAM and make it faster. So to read an SRAM bit, the associated bit line and its inverse are pre-charged to VDD/2. So let's say we want to read this bit in red right here. So we're going to start by pre-charging these bit lines to VDD/2. Next, the appropriate word line, that's this red line, gets energized and it turns on these two pass transistors, as well as all these other pass transistors on the line. And the inverter pair here is going to start pulling one of these bit lines up and the other one down. And that small differential voltage is now sensed by the sense amp down here. Sense amp senses it and then takes over and drives the bit lines very quickly to their final value. And now the data can be output. To write an SRAM bit, the appropriate word line is energized, turning on both pass transistors. Now the associated bit line and its inverse bit line bar, they're driven just to the desired logic state you want. And the strong bit line drivers can overpower the weak inverters inside the cell and overwrite the cell to the new logic state that you want. SRAM is more expensive per bit than DRAM, but generally it's way faster and it consumes less power because you're not constantly having to go through all this refresh cycling. Okay, so here's a comparison table between DRAM and SRAM. And if you just look at the memory type, they're both volatile. If you look at the cell architecture, the DRAM is way smaller. It's only one cap and one transistor versus 6 transistors. The DRAM, of course, is very dense, much higher density. Speed, DRAMs are fast, but the SRAMs are really fast. As far as reading, the DRAMs, you have a destructive read, but you have to rewrite it after every read, so it doesn't lose any data. SRAMs, it's a non-destructive read. The bit's always there until you power down. Refreshing, of course, DRAMs need refreshed. Static RAMs, based on the name static, they don't need refreshed. Cost, DRAMs are way cheaper than SRAMs. And as far as usage, you'd probably use DRAMs for your main memory, but if you needed something really fast for cache memory, you'd probably go with SRAM. So just a nice comparison table between the two. Next topic, we're going with EPROMs. EPROM stands for Erasable Programmable Read-Only Memory. And an EPROM is a type of non-volatile memory. This means it retains the data even when the power is removed. So the original EPROM was invented way back in 1971, almost by accident. The development of the EPROM started out as an investigation into a faulty integrated circuit where the gate connection to a MOS transistor was broken, kind of like what I show down in the lower right corner here. As it turns out, the stored charge on this isolated gate was changing the properties of the underlying transistor. This concept of stored charge on an isolated gate was adapted and modified to create the EPROM. So a simple cross-section of an EPROM is shown here. And it's similar to a conventional MOS device. except that it has two gates. The top gate is the control gate, and it's connected to other circuitry just like normal. The bottom gate is the floating gate. The floating gate is used to store charge when the device is programmed. And programming is accomplished by applying a high drain to source voltage and then turning the device on using the control gate. This causes excessive amount of current to flow. It creates what's called hot electrons, very energetic electrons, because you have a high electric field between the source and drain. So you get a lot of electrons flowing here, and these hot or energetic electrons cause impact ionization, sending more electrons off in all directions. And some of these electrons are going to have enough energy to pass through the lower gate oxide, and they accumulate on this floating gate. And since the floating gate is surrounded by an insulator, this charge is trapped. This negative charge can stay there long after the programming voltages are removed. And the presence or absence of this charge can be detected by the threshold voltage of the transistor. A programmed NMOS transistor with a negative charge on its floating gate will have a much higher threshold than an unprogrammed transistor. Now, this difference in threshold can be read as a binary 1 or a binary 0. Devices can be deprogrammed or erased by exposing them to ultraviolet light through a clear window in the top of the package. The UV light creates ionization within the gate oxide, allowing the charge on the floating gate to dissipate. Now, this method of erasure is not very convenient because it takes several minutes under a UV lamp, and in addition, it erases the entire memory at once. And you can see what an old-fashioned EEPROM looked like with the clear window down in the lower right corner here. So in 1978, an improved version of the EEPROM was created to address this issue. And the new EEPROM is called an EEPROM or E squared PROM. This stands for electrically erasable programmable read-only memory. And from a simplistic cross-section, it looks very similar to the original EEPROM. They still have the floating gate and a control gate. The main difference is the lower gate oxide is much thinner, something probably less than 200 angstroms or so. And programming is still done by the injection of hot electrons, just like before. However, erasing can now be done electrically on an individual cell basis by applying a high positive voltage to the drain while grounding the control gate. The resulting electric field pulls electrons off the floating gate by a phenomenon known as quantum tunneling, also called Fowler-Nordheim tunneling. And I'm not an expert on this. You're going to have to ask a physicist about tunneling. Don't ask Dave. He's too old. He'll tell you something about picks and shovels or something like that. I'm picking on Dave. He's my target. Anyway, Fowler-Nordheim tunneling is how you discharge all the charge off that gate. And I think it has something to do with electrons have a statistical cloud, and if some of that cloud, the tail is way over on the other side of the barrier, sometimes the electron is over there, and who knows how it actually gets through the barrier. Anyway, at least you've heard the term now. The non-volatile nature of this memory, coupled with the ease and speed of reprogramming and the resistance to mechanical shock, makes EEPROM the device of choice for flash memories and memory cards used in many audio and video devices today. All that stuff that you have on your phone is probably stored in EEPROM right now, or an EEPROM structure. It's really a flash, but flash is made using EEPROM and configuring the way the EEPROMs are hooked up. Okay, next subject. Now we're going way back, and I have an example of this sitting right down the corner over there by Jonathan. This is magnetic core memory, and you might have heard of it. Core memory is a type of non-volatile random access memory that was developed way back in the 1950s. and it was used until somewhere in the mid 1970s. So this is what was used for all the moon landings. Core memory was, all the navigation computers, it was done with core memory. So the bits, individual ones and zeros, were stored as the direction of the magnetic field in small ferrite rings, aka toroids, and these rings are called cores. The direction of the magnetic field could be altered by passing a large enough current through the center of each ring to flip the magnetic field. Clockwise magnetic fields were considered to be a logic 0, and counterclockwise were considered to be a logic 1. The cores were arranged in an XY grid pattern with multiple wires running through the center of each ring. To write a bit, enough current in the correct direction would have to be passed through both the X wire and the Y wire to flip the magnetic field. The current in a single wire by itself wasn't enough to flip the bit. So what I show here, this is a zoom in of what these magnetic core memories look like. These things are really tiny. You gotta just see the example. You can barely see these things even under a microscope. They're super tiny, and can you imagine trying to weave these wires through here? So this is what it looked like, and to program it, again, you'd have to force current. If we wanted to program this core right here, these two currents would be additive, and that would be enough to flip this bit. But none of these other bits are going to flip because you're only seeing half the current. So this writing process was also part of the read cycle. Every time a core was flipped, it induced a current pulse in a sense wire that let the system know that a flip had occurred. And that's this green wire. And you can see I've kind of wound this green wire all through every one of these cores here. And that's what you're seeing on this picture here. And if you attempt to write a bit, the current pulse on the sense wire let the system know the previous bit value. If you saw a current pulse, the bit was opposite to what you were trying to write. And if you didn't see that current pulse, the bit agreed with what you were trying to write. So this process of reading a bit was destructive because you're messing with the magnetic fields. So additional circuitry was added to rewrite the bit after every read. So it gets really complicated. So when not being written or read, cores maintained their value even if power was removed. This is non-volatile. Magnetic core memory was phased out in the 1970s in favor of electronic memory. This stuff, though, is really super rad hard, though. It was the big thing about core memory. It's super rad hard and very reliable. However, it takes up a lot of space. I just wanted to show this picture. This is a 1K memory module, 1K, only not a gigabit, 1K. So, and it kind of looks like woven cloth. And again, when you leave the room, take a look at the show and tell item down there. It's amazing. Okay, so enough of ancient history. Now we're going to talk about FRAM or FERAM, it's sometimes called. This stands for Ferroelectric Random Access Memory. And this memory cell is made from one transistor and one capacitor, very similar to the DRAM cell. And you can see what this memory cell looks like down in the lower right corner here. However, unlike a DRAM, FRAM is non-volatile. And instead of storing the ones and zeros as charge on a cap, FRAM stores the information as the value of the capacitor itself. The dielectric in a ferro cap, and notice there's a little difference to the symbol on this cap here. It has this extra line through it. That's the symbol for a ferro cap. And it's made out of this material. It's abbreviated PZT, and I'll give you the chemical composition in a minute here. And this material can alter its dielectric constant by roughly 10x after being exposed to a sufficient electric field. Now, this property creates two states, a high-value capacitor and a low-value capacitor, depending on what polarity field the cap was last exposed to. So how does this PZT material work? Well, PZT is known as lead zirconate titanate, titanate. I think I got that right. And it's a piezoelectric ceramic material that can convert mechanical stress into an electrical charge and vice versa. It's an electric dipole with two stable states. Now, if you place a strong enough electric field across the crystal, you can cause it to transition between these two states. And you can see what you're moving. You're actually moving some atoms in here with the electric field. And it's kind of the combination of the titanium and the zirconium that you're moving around here. As it turns out, one of these states has about a 10x higher dielectric constant than the other state. So if you can build a cap using PZT as the dielectric, the cap will have two stable values, a high value and a low value. By the way, on this next drawing, I've made a little abbreviation. I'm going to draw it. If we pull this atom down, I'm making it look like this rectangle with the dot at the bottom. If we pull the atom up, I have a rectangle with the dot at the top here. So the diagram below shows a parallel plate capacitor with PZT crystal as the dielectric material. So if we apply a positive voltage, and we're talking like 1.5 volts across the cap, the atoms in the dielectric align to give a high dielectric constant, and this gives you a high value cap. If we take that same cap and we apply the field in the opposite direction, the atoms align to give you a low dielectric constant and a low value cap. And you can see there's some hysteresis here. So due to this hysteresis, the two states are both stable at 0 volts. And what this means is the cap will remain in its programmed state if no voltage is applied or if the power is removed. That makes it non-volatile. So the bit can be read by energizing the word line here and then raising the voltage on the bit line, and that forces a pulse through the capacitor to the sense amp, forces a current pulse through the cap to the bit line. If the cap is a large cap, the current pulse is going to be bigger. If the cap is a small cap, you're going to get a small current pulse. So this current pulse can be read by the sense amp as either a 1 or a 0. Again, you're trying to read the cap here. So this read process is potentially destructive because you're applying some voltages to the ferro cap. You might make it flip state. Therefore, each bit is rewritten after being read, very similar to what was done in core memory in the 1950s or 60s. So just to summarize, FRAM, ferroelectric RAM, contains no iron, no matter what the name says. There's no iron in ferroelectric RAM. And it's not affected by magnetic fields, again, no matter what the name says. The name ferroelectric RAM was coined in the 1950s due to its similar operation to magnetic core memory. This material, this PZT material, was actually developed in Japan in 1952, and it's used on a wide variety of sensors and pressure sensors and a bunch of other things, but using it as a variable capacitor in a RAM really didn't catch on until the late 1990s, early 2000s. But the material's been around for a while, and that's where the name came from, because it looked a lot like magnetic core memory. The packing density of FRAM is not great because it currently needs some pretty big caps for the sense amp to distinguish a 1 from a 0. So due to this undesirable packing density, FRAM is currently only available in smaller arrays, something less than maybe 4 megabits, and it's fairly expensive. But FRAM is a low current memory solution because there's no refreshing needed, it's non-volatile. And unlike an EEPROM, the voltages used to program, read, and erase an FRAM, they don't cause any oxide damage. We're talking like 1.5 volts here. Therefore, FRAM can be programmed and erased trillions of times with no reliability issues. Not so with EEPROM. You got to really put a lot of voltage on an EEPROM. So Texas Instruments has been working with a partner, Ramtron. Ramtron got bought out by Cypress in 2012. But TI was working with Ramtron since the early 2000s to develop an in-house FRAM process. And here's a summary TI published comparing they're FRAM with EEPROM and flash. And one thing I noticed right away, you look at these voltages here, you only needed 1.5 volts to write the FRAM, and you need like 10 to 14 volts to write the EEPROM. So you're not stressing those oxides. But the one that really caught my attention was this one at the bottom here, resistance to gamma radiation. I'm pretty sure this is what a TI is using for all their rad-hard or rad-tolerant products right now, if they need an onboard memory. The last topic I want to discuss today is ReRAM, sometimes called mem resistor. I believe this technology has a lot of potential for the future. However, to my knowledge, it's currently not in production. ReRAM stands for resistive RAM, and it's a type of non-volatile random access memory. The memory cell is actually very simple. It's basically a top electrode and a bottom electrode separated by a variable resistance layer. The value of this resistor can be altered by applying various voltage levels. The logic levels are encoded as the resistor value. This VI characteristic in the lower right corner here demonstrates how this technology works. The resistive material separating the two electrodes has two states. The low resistance state that we're going to call LRS, and the high resistance state that we're going to call HRS. Applying a positive voltage across the electrodes forces the material into the low resistance state. That's this red line here. And it will stay in the low resistance state until you get a large negative voltage, which causes the material to transition back to the high resistance state. That's the blue line right here. So once again, this hysteresis ensures that each state is stable. If the power is removed, the resistor will stay at its last programmed state. So that makes it non-volatile. So how does this work? So there's a whole bunch of research going on in this area, and I can't even begin to show it all. But I'm going to try to give you a simple example as an overview. So one of the materials currently being experimented with for this variable resistance layer is called hafnium dioxide. And you may have heard of it before, maybe not. Hafnium dioxide is a high K dielectric, and it's currently in production as a gate oxide on many advanced FinFETs. So this is not some exotic material. This is something that's in fab right now, in production. I'm sure it's all over the place at TSMC. Hafnium dioxide is great because it's a high K dielectric, and it's very similar to silicon dioxide. It's an insulator. So how does an insulator become a variable resistor? And the answer to that is you do something you're never supposed to do on an IC. You purposely apply enough voltage across the electrodes to break down the oxide. Okay, so let's go through the procedure here. So you start here with your two electrodes and your insulator, your hafnium dioxide in the middle here. You move over to this next one in the middle here, and you apply a large positive voltage to actually break down the oxide. And what you're doing is you're creating oxide vacancies here. You're actually stripping off some of the oxygen ions and moving them up to this top plate up here. And if you look down the lower left corner here, I show what the crystal structure of hafnium dioxide looks like. This is very similar to the crystal structure of silicon dioxide. And if you apply a high enough electric field, you end up ripping some of these oxygens out of here, leaving vacancies behind. And that's what we're doing here. We're creating a whole bunch of vacancies. And the oxygen atoms, as you pull out of those vacancies, they tend to pile up at this top plate up here. So electrons can now jump from vacancy to vacancy to vacancy and conduct between these two electrodes. This is called the low resistance state. Now we move over to the third panel here, and we apply a large negative voltage. And what happens? Some of those free oxygen ions, well, they're going to backfill some of these vacancies, not all of them, but just a few. And this blocks the majority of the paths for the electron conducting between the plates. So this is known as a high resistance state. And supposedly, you can jump back and forth between these two states. And this state is considered the logic 1, the low resistance state, and the high resistance state is considered the logic 0. So here's what a ReRAM memory array might look like. It still has the familiar word lines and bit lines that we saw back on DRAMs and SRAMs. And it has the potential to pack very densely because these cells are really tiny. And it's fairly low power. It's non-volatile. There's no refreshing needed. However, because every bit is connected to every other bit through resistors instead of transistors, writing and reading can get a little tricky here. Now, for time reasons, I'm not going to go through a long explanation. However, I would like to show at least how to write one bit. Let's say we want to write this bit in red here, and logic location 1, 1. So we need to pull the word line high, and we need to pull the bit line low to get enough voltage across this resistor to force it into the state we want. But we don't want to write any of these other bits that are around here. So to ensure that, what we do is we pull all the other word lines and bit lines to the midpoint of these two voltages. So now none of the other resistors see the full voltage delta. They're only going to, worst case, see half the programming voltage. And that's safe. It's not enough to make the thing flip. Similar tricks have to be done when you're doing a read for this. And I'm not going to get into that, but I just wanted to show you it's kind of tricky now because you've got this big array of resistors. Okay, so ReRAM summary. ReRAM is not in production yet. However, extensive research on materials and techniques is currently underway. This technology has the potential to create very dense, low-power, non-volatile random access memories with reasonable read and write speeds. Some research is even being done on ways to encode multiple bits into a single memory cell by programming different resistor values. This, of course, would increase the packing density even further at the expense of a more complex sense stamp. Instead of a 1 and 0, now you have a 0, 0, a 0, 1, a 1, 0, and a 1, 1. So in my opinion, ReRAM has the potential to be an important memory technology in the future, but it's still really under development. Okay, conclusions today. Digital memory is an important part of most modern ICs. Even so-called analog ICs tend to rely heavily on digital memory for setting configuration bits. In addition, the standalone market for mass data storage, like solid-state drives and SD cards, is rapidly increasing. I hope my talk today has added to your knowledge of how various digital memories work and given you some background on where the industry has been and maybe where it's heading next. Thank you for your time. There's a glossary at the end of this. If you have any questions, you can look through the glossary.